Hello, Math 30-1. This is an investigation of exponential functions. And in this first slide, it's just a bit of a concept map of what we're going to be doing. And in our travels through Math 30-1, you have developed a major, skill set of different functions. We've had polynomials and radical and rational and trig. And so this is just another function that you want to better understand. And a lot of the things that apply to it, we don't want to see this as a separate, we want to see this as a separate type in our family of functions, but the things that we've done to our functions, stretch them and move them, vertically stretch them, take the reciprocals, take the inverse of them. We want to do those things to this function as well. So what will we learn about this? And there is an investigation in your textbook that you could do that as well. And we're just trying to get a deeper understanding of these areas of this function. So what do their graphs look like? And how does it differ depending on different things? What are its characteristics? But what if we were asked to transform them in the same way we did before? What if we were to reflect them in X, reflect them in Y, vertically stretch, horizontal? What happens to it when it looks like that? And how do we change the equation when we state those things? And finally, how do we solve equations that are exponential? So this is our investigation of exponential functions. What does it look like when you have y equals 2 to the x and 3 to the x and 4 to the x? And so clearly, multiplication is a repeated addition, and power notation expressing in repeated multiplication. And we want to be clear that 4 is the base and 7 is the exponent, and so an exponential function, when we're looking at those, is where our variable is in the base. Just like we talked about with an exponential equation, in the same base. Examples of exponential functions are 2 to the x and so on, as we see there. A base 2 and a base 10 and a base 3. These are non-examples of radical functions, and they are things like x squared and 2x plus 1, obviously quadratic and linear. All right, so making sure we're clear when we see it, what's exponential? That x must be an exponent, and this is important. These restrictions aren't just to be ignored. You can't have a base b value of 1, because then the repeated multiplication would just be 1, 1, 1. And c has to be greater than 0. In an exponential function, you can't have a base that's negative. Okay, so when we analyze the graph, look at this for y equals 2 to the x. Plug in those values and then come back and look and see what you get. But think of I think it's important to kind of do this in your head. What does 2 to the minus 4 look like? What does 2 to the 0 look like? What does 2 to the 1 look like? Now that you've done that, you come back and you ponder and you plot as you do the graph, and you can see, you can see as you plot the graph that you're ending up with a graph that has an asymptote, and as it goes to positive infinity, it just gets taller and taller and taller, that it grows exponentially, right? So y equals 2 to the x. And everything in between there fills in as well, as we saw the 0.25 and the 0.5 and the 0.75. And you can see when you went to negative values, what it does, it gets smaller and smaller and smaller as the base gets bigger and bigger and bigger, from 2 to 4 to 8 to 16. So if we draw in this nice smooth curve, we get a graph that looks like that. What are its characteristics? Well, we notice, as it says, rapid increase. The y-intercept is 1. It has, move that over, move this down. It has a horizontal asymptote of y equals 0. That's important. The graph increases slowly as x is less than 0. So as it moves this way, what it's saying is when x is less than 0, it increases really slow, but when x gets bigger than 0, it goes a lot faster. Okay. So again, understanding better, what difference does it make when the bases change? As you go from 2 to 3 to 4, we want to ponder the questions. We want to ponder the questions, well, what effect does the base change have? Then you could look at it on your graphing calculator, you could plot the points, but what characteristics remain the same? If you plotted them on your calculator, and I'm just going to move this down now, if you plot them on your calculator, you'd notice they look very similar, but they are different, and it would be good to ponder why. Well, clearly they all have the same y-intercept of 1. None of them have an x-intercept, and that's because if you think about number sense, how could you make y 0? What exponent would you put on any of those bases and make 0? So you have no y-intercept. The domain, they're all a member of real numbers because there's nothing you can't put on exponent. The range y such that y is greater than 0, we have that asymptote. They all have that asymptote at 0. So they all have that similarity. I wonder why 4 is taller and 3 is taller than 2. We have other kinds of exponential graphs, and they are called exponential decline or exponential decay. Graphs of this form are where the bases are less than 1. And I probably shouldn't get into applications, but we'll talk more that if you have a base that's negative, right? Excuse me, I didn't mean to say the base is negative. I was looking at this different version, and I don't want you to get thrown off. These two statements are equivalent statements. It's just saying that if you wanted to, and I'll just show you on the board, if you wanted to, you could express, for example, if a was between 0 and 1, you could say, well, what if I had y equals 1/2 to the exponent x? That would be in this statement. You could have the equivalent situation where somebody says, oh, no, that's not what I meant. What I really meant is 2 to the minus x. Well, clearly that negative you could put to the 2, and that would be equivalent to this. You could write it either way, where a is greater than 1, but you have a negative exponent. It makes more sense to write it the first way, but I don't want you to be thrown off by different ways of writing it. Now, if you have it, when you think of what happens when you put exponents to, what happens when you put exponents on top of that base of 1/2, well, clearly it does something different than what it did before. When you look at the table of values that we had there, when I put a -3 on top, I end up with 1/2 to the -3, which would be 8, and -2 on that exponent would be 4, and so on. So you get the same values, but negative values, the y values are the same as they were for the positive corresponding values. So you get the same graph, but it's basically reflected around the y-axis. Maybe that has something to do with the fact that if you wrote it this way, you really are taking it from f at x to f at minus x. So it's a reflection in the y-axis if we start connecting. All right. Well, as we can see, this is declining by 1/2 every time, right? And some of the characteristics still has a y-intercept of 1, still has an asymptote. It kind of decreases slowly there and decreases steeper here, and that asymptote of y equals 0, okay? So the main thing we want to get out of that is that when our base is more than 1, things will grow, and there is going to be a multitude of applications. But if your base is more than 1, just like in compound interest in interest in banks and things like that, so money's going to grow if your base is more than 1, because you're going to be multiplying by a number more than 1. If the base is between 0 and 1, the graph will go down because it will be decreasing, and you'll have a graph that looks something like that. So that is a decreasing function, and I don't want us to get too caught up. I don't see that very often, but I do want you to see it in different ways. So this version of it, when c is between 0 and 1, this is a backhanded way of saying that, right? So this is an exponential decay situation. What happens when c is 0? Well, when c is 0, that's crazy. It's just a 0 function because you'd be multiplying by 0 all the time. So we definitely can't have that, right? And if c was less than 1, then you'd be multiplying by a negative and so on. So we don't have anything less than 1, or sorry, less than 0 or 0, okay? So you have most of this slide. So just complete the characteristics here based on what you've learned. Are you at peace with these characteristics? And I'm just going to quickly go through them, and you can pause and write them down and ask about these if you're not at peace. So domain is all real numbers. The range is all positive numbers. The parent graph passes through 0, 1. And if c is 0, it is an increasing function. If c is greater than 1, it's increasing. If the base is between 0 and 1, it is a decreasing or decay. And I wouldn't mind you, this is called growth, and this is called decay. So if you could ponder that or consolidate that. And the graph approaches but does not cross, it's that horizontal asymptote. So that was something that we hopefully got out of that. Now consider the number of pairs below. Write each of these numbers in a pair that would lie in each of these graphs. So which point matches each of these graphs? Ponder and then come back. So who matches this one? Number 4. Who matches this one? Number 1, number 2, and 3. Okay. If you're not at peace with that, ask tomorrow. Write the equation that models the graph of y equals a at x. Right? So clearly, as you ponder this and you decide what you're going to write for that, you want to think about what happens at each point. So with this one, clearly at 1, it's at 6. So exponentially, you'd assume that that could be y equals 6 to the x. With this one, if you go backwards 1, at minus 1, it's 3. So that should mean that my base was 1/3, because all we were dealing with is the simple y equals a to the x. What's the y-intercept on this graph? Well, what do we do for the y-intercept? For the y-intercept, we let x equal, for the y-intercept, we let x equal 0. So on this graph, we let x equal 0, and we get a to the 1 plus b. So the y-intercept must have been a to the 1 plus b. Bit of an application. So the intensity of a light stage decreases exponentially with the thickness of the color lens, and can be calculated by using this formula here. You used to start out with 1200, and then n is the number of colored gels used. So what is the intensity of light after 2 gels are added to the mix? Well, we'll put a 2 in there, and obviously we get 768 watts. What if we had, in this case, 4 gels? What we would have 491.5 watts. An application, notice that the base is less than 1 and it's decaying. It's getting less and less as the number of gel coats you put on top of the lens. What is the domain of this situation? What would be allowed to do? Well, n must be a whole number for sure, and I guess we could keep adding them as long as pretty soon it's going to be dark because we'd shut out so much light, but that would be it. All right. We will chat tomorrow about these notes and whether you have any questions.